I'm your host, Ed Porter, and welcome back to Transmission. Two-thirds of industrial energy demand is heat, not electricity. A significant share of that falls in the medium temperature range, the frying, drying and applying that runs through paper mills, breweries, food plants and chemical facilities. Most of it still runs on gas. In Germany, where natural gas dominates industrial process heat, that dependence is acute. There's an alternative. Thermal storage converts electricity into heat during low price windows, stores it and dispatches it when the factory needs it, cutting the gas bill substantially. My guest today, Alex Robertson, CEO of ENERGYNEST, joins me to talk us through the technology and why the grid is the thing standing in the way. If you're looking at projects in Germany, Modo Energy's solar and battery forecasts are live, or you can ask Co, our AI analysts, any questions that might arise from this conversation. Link below. Let's jump in. Hello, Alex, and welcome to Transmission.
Hi, Ed. It's great to be here.
Our pleasure to host you, and very excited to get into thermal storage today. What is one thing that everyone gets wrong about thermal storage?
Yeah, thermal energy storage. I think probably the biggest thing that would help people understand it better is if they thought of it more or less like normal battery electric storage. It's got so much in common, but it's cheaper and better.
Okay, cheaper and better. That's a great start. And you mean it's got so much in common in that it's kind of what are the characteristics that make it so similar to battery energy storage?
Well, let's start with the big difference. We turn electricity into heat and then store it as heat and then deliver it to our customer as heat. We never go back to electricity. So it's one way in that regard. So a traditional electrochemical battery, obviously you go from electricity to your electrochemical reaction, lithium-ion reaction, and then back to electricity. So we don't do that. And I think for a lot of people, the kind of one-way nature of it makes people think, well, this is a very different beast. But actually, the way the electricity markets work, it functions 90% the same on the market as battery electric storage does. But you have a bunch of benefits. We can dig into them if you like.
Okay. Well, the thing I really like, right, is that whenever you hear about any kind of technology, you should kind of think about the energy side of it. And if somebody tells you that there's 10 stages of it being converted from one thing into another thing, like every time you make that conversion, you're going to lose energy in that process. There's going to be inefficiency. And so you kind of automatically get quite skeptical. But as you're saying, so it's sort of from electricity into heat and then heat gets delivered as heat. Well, there's kind of fewer steps in that, which to me already feels like an advantage. Versus sort of other sort of techs coming out. But let's then just talk about how the thermal battery actually works. And I know today you've brought a prop as well, which I love. So maybe you want to start off describing the system itself, and then let's talk about the prop.
Yeah. Okay. The system takes electricity from the grid, converts that electricity into hot oil, pumps this hot oil into one of two different places. It either goes to a block of concrete and makes the block of concrete hot, that's the battery, or it goes to a heat exchanger with the client, and we deliver then the client either hot oil or steam or hot air or however they particularly want their heat. They can have it how they like. So you've got three elements to the system. You've got the electric heater, you've got the concrete block of storage, and you've got the heat exchange interface with the client. And the client for us will be an industrial heat consumer. Before we'll come back to the technology, but I think we've got to probably start with understanding who the client is for us. Okay. And that would be industry. So a common misconception about industry, or just a kind of not known fact, is that at least 2/3 of industrial energy demand is actually heat. So if you go to a paper factory, they'll have some electricity demand for running some machines, running their computers and lights and so on. But the vast majority will be gas that they're burning to dry the paper. And that's true in, cooking, in industrial, cooking, food preparation, food and beverage, brewing beer, making spirits, chemical processes all over the place. There's huge amounts of heat being used.
And it's not all exactly the same, right? So you have low grade heat, high grade heat. Obviously, some parts of that sort of spectrum are much harder to produce than others.
Yeah.
So where do you sort of see your solution fitting in?
Yeah, so you've got a range. You've got kind of space heating, which is sub 100 degrees territory, and that is the domain of the heat pump. And then at the other extreme, you've got the very high temperature heat, which is extremely difficult to electrify. Difficult to electrify, maybe not extremely difficult, but difficult, which is making cement or steel, electric steel furnaces and so on. In the middle, you've got this huge demand of what we call medium temperature heat, which is typically delivered in the form of steam. And that's, frying, drying, and applying. So cooking stuff, all 200 degrees Celsius, classic kind of cooking temperature ovens, frying your oven chips and so on. Drying stuff, there's an immense amount of drying that goes on, like paper being the biggest application, but everyone's drying stuff, and then applying and using chemical processes. So this is medium temperature heat. You're typically too hot for a heat pump. Heat pumps are moving up into the bottom end of that territory.
I was going to say we see that growth from heat pumps, right? The heat pump from 5 years ago is not the same as the heat pump today. They are kind of eating into that.
They are. So they're coming up from the bottom. But the thing with heat is the higher the heat, the harder it is to deal with. And doing anything with heat at 1,000 degrees is quite a challenge. You need to use very specialist materials. You have all kinds of materials do all kinds of funny things when you heat them to 1,000 degrees. So you've got to be very careful. So we're operating a range. Our product, our sweet spot is between 150 degrees and I would say 300 degrees is kind of our sweet spot. And that's the range where pretty hard to do it with a heat pump, if at all. But it's still very cost competitive to do it to store energy as heat.
Okay.
Right. So the customer want heat, and they use a gas boiler. Most customers would use. We're mainly in the German market, and the main heat source for German industry is gas boilers. Gas boilers are great. You can fix your gas price for 2 or 3 years if you like. You can get a nice big grid connection to the gas network. 20 megawatt gas link, no problem at all. Gas boilers not very expensive. You turn it on and off when you like. It's a great solution. Problem is, it's increasingly expensive, and obviously it's not compatible with the net zero future. Mm-hmm. So yeah, we're going into German factories and augmenting their gas boilers with our solution, our power to heat solution. So what they want is heat. So why do you need the storage? Is the next question. And the kind of starting point of understanding is that on average, gas is a lot cheaper than electricity. Even now, even with the Straits of Hormuz crisis that's going on in the Middle East, gas is still cheaper per unit of energy on average. But we're not interested in the average. We use storage to decouple the thermal demand of the client from the market price of electricity. And when you do that, when you buy electricity only when it's cheap, then suddenly you can come in well below the cost of gas. Mm-hmm. And that's what we're doing. Okay.
And the way that, so it's quite interesting, right? So because you have storage on site, you're sort of shifting in time to try and get low cost electricity from a cheaper period and then make that more competitive with gas by avoiding those high price periods. The heat pump example, like they get around this in a different way. They use the electricity to borrow heat from elsewhere,
exactly,
which is kind of how they compete. So so we're essentially trying to say that if you're just going to run like an immersion heater, so just like straightforward electricity to heat, that's going to be expensive.
Yeah.
But if you try different ways of getting heat, either by shifting through time or by borrowing heat from elsewhere, then you can be a bit sort of canny about this.
Yes.
And you can find solutions where they lower costs. So before we kind of go into the sort of economics and technical side, I know you've brought a prop, and I love a prop, so I'd love to sort of see what we've got.
Right. So I think you have to ask the question, why thermal storage? Why? And I ask this question all the time. Why do the storage? Why not use a battery, a traditional electrochemical battery for this? Mm-hmm. So I brought an example here. This is a piece of our concrete. We use a special formulation of concrete.
Okay.
We call it heatcrete. You can touch it.
Yeah, well, thank you. But just making sure that people who are listening to this know what I've got. So I've got in my hand, I've got a sort of, it's like a cylinder the size of a mug, and it just looks like a regular bit of concrete, if I'm honest, with HL2B written on it.
Oh, don't read that out.
Yeah, sorry,
That's the
top secret.
Top secret letter. Yeah.
So
I mean, it isn't
what is that?
too far. It's a concrete that's been optimized for thermal conductivity,
Okay.
so its ability to transport heat, and to some degree for thermal capacity, its ability to store heat. The storing is the easy bit. Anything big and heavy, bricks, stones, sand, all that stuff stores heat very well. But the conductivity is the challenge. And the way you improve the conductivity is you minimize the amount of air bubbles that are on concrete. So normal construction concrete is actually very porous. And you also choose an aggregate that has a good thermal conductivity, which is the stones that go into the concrete. So that's what that
there's less air in this block of concrete than a regular block that you would see somewhere else.
Yeah,
okay.
And it uses a special quartzite, a quartz-based aggregate that is
which is the stone that I can kind of see in it. Yeah.
And we get that in Germany, and that happens to have good thermal properties, good conductivity.
Well, there's a nice story in there, right? So, is your supply chain for manufacturing this? Is it all very much sort of within Germany for German industry?
It's boringly European.
Okay,
it's mainly Germany. We have one factory that we use in Eastern Europe, and one supplier, a few other suppliers around Europe, but it's entirely European. It's entirely local. It's very basic ingredients we're using. So I mean, this is what brings us to the comparison with these batteries. So I brought along. So
15
here we see
20 batteries.
There are 18.
Lined up. 18. Okay.
So not a bad bit of estimating at site, Ed. There are 18 batteries there, and the link I'm showing you here is that the energy storage capacity of this block of concrete heated in the temperature range that we heat it is equivalent to these 18 batteries.
Okay, that's interesting.
So then you can ask yourself, which one of those do you think is cheaper?
Yeah, well, I mean, I assume that is just a regulation block of concrete, so it's got to be the concrete.
It is indeed the concrete. Which one of those do you think is manufactured in Europe?
It is. Well, I know the answer to this because I've been listening along to this episode, so I know it's the concrete block.
Yeah, and which one of those has no kind of difficult to procure materials like lithium and so on? Maybe you don't know that about the concrete, but I assure you it's relatively standard stuff.
I was going to say I don't know about the concrete. I would say batteries. Yes, I mean, definitely correct for sort of your nickel, manganese, cobalt batteries from 3 to 5 years ago. I think less so with lithium-ion phosphate, the LFP, that's more used today. As we go into sort of sodium-ion in the future, potentially again. But this is the nature of competition, right? You're providing one solution to get electricity into heat. The other types of competition out there in terms of battery storage is all at the same time. At the same time as you're working out how to make your concrete block have fewer air bubbles and have a better conductivity, the battery industry is working on exactly the same stuff. That's the wonderful nature of competition.
It is, and I'm sure you'll ask me later. Actually, this is not about me bad talking electrochemical batteries, because they're also a miracle, basically what's been achieved there, and they're an essential part of the grid ecosystem. So I've got nothing against electrochemical batteries. The final advantage I would say about thermal over the electrochemical alternative is the degradation topic, and I think the degradation of electrochemical batteries has improved a lot and is much better understood and much easier to model. Nevertheless, the concrete has precisely the same thermal capacity after 25 years of cycling as it does on day one. And
do you not get sorry to ask a GCSE geography question here, but does that not, you remember the like freeze thaw weathering and sort of onion skin from those days when you sort of, if you heat up stuff and then cool it down and heat it up and cool it down,
does it crack?
Yes, exactly. Like the sort of material engineer in me says, right, cracks start to form, cracks start to propagate. Surely that's a problem. I mean,
that is one of the key kind of design considerations in how we design our concrete battery is to prevent cracking, but actually a certain amount of cracking is completely acceptable. But prevent and manage cracking, and the thermal expansion. So you're exactly right, and that is what that is probably our on the tech side of the concrete part of our secret sauce about how we manage that. Okay, well, I won't ask too many questions about it because don't want to give away the answer. don't want to give away the answers. Okay, so let's scale up, right? So we've got this sort of mug-sized block of concrete. Let's say we're going to the frying, drying, and applying, which I do hope is the name of this episode. We shall see. We shall see. But let's say you go to a sort of a standard client, and then maybe they've got sort of a need for a standard industrial load of heat.
what is the sort of scale up size of that mug-sized piece of concrete? Is it as big as, say, this table? Is it as big as a double-decker bus? You know, where does this lead?
So our battery module is based on roughly based on the proportions of a standard 20-foot shipping container.
Okay.
And that has a storage capacity of about 2 megawatt hours. And then we stack them 3 high, so you get 6 megawatt hours in the stack, and then you put as many of them next to each other as you like. So our biggest project, which is a 40 megawatt hour battery, that one actually has 24 modules. It's a bit more than 40 megawatt hour capacity. And yeah, you just stack them up and put them next to each other. So the battery itself is, you can get a sense of the scale for that. It's pretty energy dense. And the thing that makes it, that makes it particularly dense is that you're putting these things, you build these modules, literally next to each other. There's no space in between them. So you get like a single massive block of concrete that you get hot. And then we encase that block in thick insulation, so about 40 centimeters of insulation, and then a weatherproof housing. And that's the battery.
Okay.
And that, you can heat it up. We store up to almost 400 degrees Celsius, and it has remarkably low thermal losses because
yes,
it's well insulated. We're very careful there's no air. Like it's all, we use loose, it's insulated with, what look like traditional, rock wool insulation sheets that you might recognize from your home, a bit more specialist for these higher temperatures. And then we fill every gap with what we call loose fill insulation. So there's no airflow in there. And that thing will sit comfortably and lose around 2% of its storage capacity per day. So
okay.
It's very, very efficient.
I was going to ask that question, which is this a solution for optimizing sort of heat load within day, or do you think sort of across weeks or across months maybe? What's the typical use case?
Yeah, well, we cycle at least once a day,
okay.
And because that's what the energy markets basically pay for. So our typical battery size for your listeners who are familiar with this world would be a 4-hour battery. So the megawatt rating is 4 times the megawatt hour rating is 4 times the megawatt rating. We have a much lower, the cost of additional modules is pretty marginal. So there's no reason, we could do an 8-hour battery without a huge increase in cost. That's one of the favorable things about the technology. But the truth is that the market doesn't pay for it. The additional revenue that you get from the energy markets from the 8-hour battery, at least we don't see in Germany, we don't see much of a marginal revenue there. So our technology is currently focused on daily cycling, just like a normal battery, electrochemical battery on the grid would do. There are other people in the thermal storage space offering longer term batteries, and that there's something because the storage medium is so cheap, going to longer storage durations it definitely lends itself to thermal storage, but I still haven't seen a case for it yet.
Okay. And we have some sort of fascinating trends that we're starting to see coming through in power pricing across Europe. So I know we're talking a lot about Germany here, but I've just come back from Madrid where we were running workshops on power pricing in Madrid, and I think there's some great stat that the average price for the first quarter of this year, the second quarter of this year, was 7 hours at £0 during the middle of the day, because there is just so much solar and there's not really anywhere to put it. So effectively you get this kind of great opportunity. So your 4-hour system today, maybe it'll be an 8-hour system, and someone will just be block shifting that energy to the evening period, let's say, when obviously solar's not running.
Well, there's one other positive difference about the way we operate on the energy markets, which I draw your attention to. So typically industrial customers have relatively constant load. So they're running their machinery 24/7. So that means, although the battery is theoretically a 4-hour battery, it's constantly being drained into the factory. Now that is not the case for a grid connected, in front of the meter battery, electrochemical battery. So although it's a 4-hour battery nominally, we can essentially charge it for 6 hours, because you've got a constant flow of power moving out of the battery into the factory. So that's actually part of the reason why longer durations are not needed, because although it's a 4-hour battery, it really covers the use case of a 6-hour battery. The other thing, I think there's one of the strongest. So for the topic of industrial power to heat in general, with whatever storage technology or whatever technology you're using, has a really important role to play in managing seasonal variation. So the way we run our system is our customers do not typically decommission their gas boiler. We run in parallel with the gas boiler. We would electrify between 50 and I would say 80% of their thermal demand, but they keep their gas boiler there for the last 20%. And the reason they do that, there are two reasons. Firstly, industry is conservative and they want a backup, which I can understand. They want to, they're like a bit skeptical of this electrification world, and now
what is this block of concrete going to be doing? Yeah.
We'll keep our gas boiler that we know and love just in case. So that's fine. But we're like, well, then if you're going to do that, well, let's use that. And that means that for those weeks of the year, typically in the winter, when there is not much wind and not much sun, and you get week-long periods of high energy prices, we don't run our system. We just run the gas boiler. So you get a seasonal shift. You're doing pretty much 100% electrification in the summer because you've got lots of good solar plus a load of wind still, and then in the winter you're dropping to 50 to less. I mean, in November 2024, our back tests showed that our system in Germany would have barely run, and that's fine. Like November had like unusually high energy prices, and that's fine. Use the gas boiler.
I think for electricity systems, it's like a fantastic thing to have, something that turns up and is massive demand when there's loads of excess, and then doesn't come as demand when you get into these sort of cold, dark periods where prices are very high. That's an electricity system perspective. I think the thing that's a little bit harder is I go an energy perspective. I still see the total energy system still calls lots of energy from the gas in that November period. And so I think the electricity system would welcome you in open arms and say, this is fantastic. But I say someone thinking about the total energy system would say, we still are reliant on gas for that period. But maybe the pragmatist should say, well, actually, is it that bad to run gas for 1 month in November? If we were running gas for 12 months and we're now running gas for 1 month, well, the carbon emissions are significantly lower and we've helped the electricity system.
Absolutely.
Maybe the only hook, the only sort of tricky part is that you still have to make sure that gas system exists for all of the rest of the year. And that does come with cost.
That's true. And there is the kind of last user problem. So as we get industrial electrification up to higher levels, that last bit of gas, that gas backup becomes more and more expensive. And at some point, the system flips to 100% electrification. These are tomorrow's problems. Like I wish they were today's problems, but like we have to acknowledge the speed at which we're progressing is not fast enough. The industry is still addicted to gas. So I'm focused on getting the 80% done, and we can do that today. Way below the cost of gas. So we can decarbonize a huge chunk of our energy economy. We can save loads of money and make Europe more competitive and increase flexibility. We can reduce dependence on geopolitical events that we can't control with today's technology, and we can do it in the next few years. So that's what we should focus on. And then, the last 20% has challenges that will go with it.
I agree. I would love to. I think we've done a really good job of sort of talking about the product, talking about how it works. I think the question people are going to be sort of thinking about at home, and or maybe they're listening or watching, they're thinking, okay, this all sounds great, but how much does it cost? And what's my sort of typical payback on this? Because I've already got a gas boiler, and you're telling me I need to build all this extra stuff, and I'm going to have this additional stuff at my factory. Like, what's the incentive?
Yeah. Well, the system, based on backtesting, which means based on looking at historical energy prices in the German market, and we're mainly focused on the German market, the system typically cuts our customers' gas bill by a half. So including then the cost for the electricity and the grid fees associated with it. So the total net savings are around 50%, which is massive. And then, but there is a capex cost associated with it and other costs. So we have to hit a 5-year payback. I mean, that is, industry expects a 5-year payback, and that's what we deliver. Sometimes a bit less, sometimes a bit more, but that's where we're roughly at is a 5-year payback.
Okay. And who's like the ideal customer? Like, ideal customer walks through the door. What kind of industry is it? What kind of size? What's that perfect person?
everyone needs heat, so there's no shortage of customers in that regard. So yeah, they need to have thermal demand in our temperature range is nice. They need to have a decent amount of demand, which would be sort of 10 gigawatt hours a year plus. But again, that even a relatively small factory will have that
of heat.
Of heat, yeah.
Yeah, we might have indoctrinated all of our listeners to think about gigawatt hours in terms of electricity, but good to clarify.
Yeah. But the real thing that I'm looking for is, do they have a grid connection, or do they have a good prospect of getting a grid connection? That is, if you have thermal demand, and you have a grid connection, you are sitting on a gold mine. Mm-hmm. I mean, it's as simple as that. Like anyone, we talk to customers and they're like, oh yeah, we've actually got a 10 megawatt grid connection. We only use 3 of it, but we could switch on the other 7. And I'm like, you could make so much money with those 7. How can you sit there and not use them?
Yeah, and both aid the system and sort of save yourself money in the costs. It's a big win. One thing we have seen in some grids is that the grid connections for generation, so maybe from your solar panel or from your wind, whatever, that queue is quite big and it takes quite a long time to get through. Not all grid queues have gone the same way in terms of demand. I think one of the big things that's putting the demand side of grid queues under pressure is data centers. And so a lot of those sort of demand grid queues have really swollen in recent years. Is that something you're seeing? Are you seeing it being much harder to get that sort of demand side grid connection?
I think, it can be very tough. The nature of it's very black and white. If there is capacity in the grid at the customer's site, at the factory, then we have a project. If there's any kind of build out required, then we don't have a project. They are not in the business of building, high voltage substations to get additional connections and so on. It's not going to happen. So it's a relatively quick check, and it's particularly black and white, and we don't pursue the projects where they don't have access to grid. So there is a lot of, it's easier to find a home for 5 megawatts of additional demand or 10 megawatts of additional demand. There's plenty of pockets where that can be found. So I don't think we're competing with the kind of, 100 megawatt plus data center style connections. However, I just before I came here, I got off a call with a German DSO, the distribution system operator, where they've just rejected a grid connection for a beautiful project, a project that is like, we've got a very enthusiastic customer. They're keen to electrify. It's a good size, a good project, good thermal demand, and they can't get a grid connection.
And why does the DSO not want the solution?
Well, I think the DSO probably does want the solution because it solves a lot of the challenges they have. But in this case, there were 2 issues. One was a practical issue about whether there was space, whether there was a free field in the medium voltage switchgear at their distribution substation. Mm-hmm. We solved that. And the other one was, and this is the big one, was, we would need additional capacity from the TSO and we're not going to get it.
Yes.
And the answer, and this is where we have a system design problem, because flexible connection agreements, or particularly time-based flexibility. So this is a connection agreement where you say, I'm going to have a 10 megawatt grid connection, but during times of peak demand, I am allowed to disconnect your grid connection. There is not a framework for these yet in Germany, and they are what we need, because during periods of peak demand, electricity prices are typically high. And we're not using the grid anyway. So our system, which charges when the electricity is cheap, or charges when there's a frequency response, so balancing markets need to reduce the frequency on the grid, this typically doesn't occur when at 6 o'clock in the evening when everyone's at home boiling their kettles. So we're completely, we're heavily uncorrelated to the actual constraints of the grid. So the reality of this project is probably they don't need to do anything. They have the capacity for our system. Yeah. That's the painful thing, but they don't have a mechanism to offer us that capacity.
Yeah, and you both need the DSO to agree that your system is going to run as they expect, and then you also need the TSO to say, we understand what the DSO is saying in terms of how the system's going to run. And so when we then look at our pinch point, the kind of the connection between the two, well, we understand how they're going to interact, and this isn't going to break the system. I think we have so many, just Germany aside, we have so many examples of where there is a sort of, not slow is the wrong way, but I think people aren't being hugely aggressive on increasing utilization. They're not really worried about increasing utilization on the grid. They're worried about the grid breaking, and that's sort of top of their pile.
This needs to be the priority, is increasing utilization. Of course, grid build out is what we need. If we're going to electrify all of our energy demand, which we are, I think more or less everyone agrees that what can be electrified will be electrified. The grid needs to be expanded. But that takes decades. In the short term, we need to utilize the grid we have 100% of the time. And flexible demand, like what we offer, is a big solution to that. There's a great scheme in the Netherlands where the TSO has introduced the Netherlands has famously terrible grid queues. I mean, you just cannot get, we have so many keen customers in the Netherlands and none of them can get grid. The TSO came up with this system, which is that up to 15% of the time, they can disconnect you during peak hours and they tell you the day before.
Yeah.
Perfect. Where do I sign? No problem at all. Remember, we have a battery. We don't need to be connected 85% of the time. They could disconnect us 30% of the time, maybe 40% of the time. We wouldn't care. So that system is at the TSO level and is being broken down to the DSO level, so the distribution level. And will come into effect in the coming months, and it is going to unlock industrial power to heat in the Dutch market. Germany's just not there yet, but they need to be. I mean, it's a must in my book.
So let's do two more questions. I think one is, of the next 5 years, what has to be true to make thermal storage a success?
I think we've talked enough about grid, but that's clearly a big enabler. The next point I would talk about, would say we need to really do is we need to find a working solution for heat as a service.
Okay.
So these are capital intensive investments, and they require deep understanding of energy markets to really get the most out of them. If you have an inherently flexible asset, a battery, you need to understand flexibility. And industrial customers often don't have much money to invest, or at least the money they have to invest, they should be investing in factories and machines and their core business. And they have very little knowledge of energy markets. I mean, that's a big barrier to what we're trying to do, is that many people know nothing about flexibility, and they don't even know about how they can take advantage of the day ahead market, let alone the intraday markets and the ancillary services. So this points towards heat as a service, where instead of paying for an asset and then employing a trader to trade the flexibility and then making money from it that way, you simply buy the heat, and then someone else looks after the capital costs and the trading. Now, I mean, this is nothing new. People have been looking at this for a long time. It's just very difficult, and nobody's cracked it yet. And otherwise, we'd see, huge uptake in thermal storage and also battery behind the meter battery electric storage as well. And there's many reasons. It's very complicated. It's easy to say and easy to picture how that might work, but in the reality, to make that a kind of investable asset, it's not at all trivial. And we're very busy working on that and trying to solve that. And I think that has the potential to really unlock this.
I think some of those things have an S curve to them, so they start slowly. As they start to get scale, it's more obvious that you could kind of socialize a cost of traders working on optimizing the demand. It becomes more commonplace as a solution. Sometimes these solutions, they compound in a really nice way. Equally, not all tech makes it, so there's also that challenge that's there. I think your biggest one is that grid connection. If you could convince the electricity system operators of the properties of this, I think you would have people who'd be delighted to have that type of load on their system, because it's kind of exactly the thing that they're looking for.
I think when you look at let's say the system we electrify, say 60% of the time, a typical site. If you look at that 60%, when is it? Well, it's when there's renewables are the dominant generating source, so the electricity is cheap, and it's when there's too much electricity on the grid, so you have frequency response going on. That's when we typically, and also a bit on intraday when there's an imbalance between the day ahead and the intraday market. These price signals are working. They are causing us to charge the battery exactly when
Yes.
that we should be. So the energy markets they're currently really well structured, and the price signal is arriving at the consumer, and it works. But one price signal is missing, and that is the congestion signal. There is no, Germany has a single pricing zone with a copper plate grid approach, same as the UK, I think. So we're not getting the signal which says the grid is congested, disconnect. That there's no mechanism currently for that to reach us. And that's in terms of market design, that's the big kind of third lever that needs to be introduced is you've got the wholesale price, you've got the frequency control, and now you need the grid capacity signal. And that's coming through flexible grid fees.
It's the famous quote, if you show me in the incentive, I'll show you the outcome.
Yeah.
The Charlie Munger quote, which I think is a great example here. Let's move on to a final question. Yeah. So what is a contrarian view you hold about energy markets?
Well, I think a fundamental contrarian view I hold is that decarbonisation of industry needs to cost money. In our area, medium temperature heat is the opposite. This is an opportunity to save huge amounts of money. Gas is cheaper than electricity on average, but if you're not playing the averages game, if you're using storage to get around that, you can save huge amounts of money. And I don't think that's properly understood by people who haven't really dug into it.
So you're saying that there's a standard perception in industry that gas, even though it's sort of higher carbon, is the lowest cost way of doing things, and so therefore we must always go for, if you're just trying to go the cheapest possible route, you should go for gas. But you're saying that there's the bit that's missed, like with heat pumps, like with thermal storage, you have this option to sort of play the numbers, as it were, and that can get you underneath the cost of gas.
The first person that calls us up normally is the sustainability officer. So the starting point of all of our interactions typically is the sustainability angle, and then they see the economic benefits, and that's what seals the deal. I'm looking forward to the day when it's the CFO calling me up and saying, we've our gas prices after Trump's games in the Middle East, our gas prices have gone up 50%, and we want to save some money, and then that's come to ENERGYNEST, and let's talk about it.
There you go, right time, right place. Well, Alex, people have been clamoring for an episode on thermal storage for some time, so great to have you on. Hope we do more on thermal storage and heat pumps soon. You've been a fantastic guest. Thank you very much.
Thanks a lot, Ed.